Welcome to this video on film thickness in lubricated contacts. I'm Roland Larsson. I'm from Luleå University of Technology in Sweden. Okay, why do we then want to know the film thickness in a lubricated contact? Well, we want to determine the lubrication regime. I mean the severity of the lubricated contact. Normally we strive at getting the lubrication in here in the full film regime, but sometimes and often in engineering, in real cases, we are approaching the mixed and the boundary lubrication regimes. As I've been discussing in other videos, we are using the lambda ratio for that, the film parameter, which is the ratio of the minimum film thickness denoted by H min, and the surface roughness height, or the combined surface roughness height of the two surfaces. We are normally using the RMS surface roughness height here. As I've been saying before, it's not a perfect measure, but it's good enough at this moment. Still, I want to put a warning sign here, especially for non-conformal contacts, for elastohydrodynamic lubrication. This lambda model isn't perfect, and especially the regime limits here that the lambda should be 3 to get full film thickness, and should be above 1 to avoid boundary lubrication. It's not really true. You can run in full film even at very low lambdas, like 0.5 or so in an EHL contact. But that's another story. Let's discuss about the outline of this presentation is as follows. We will discuss how thick the lubricant film will be. We will distinguish between hydrodynamic lubrication and elastohydrodynamic lubrication. That is conformal contacts and non-conformal contacts. And for the EHL case, I will show you some film thickness equations which are easy to use and relatively accurate. And I will also discuss the main parameters controlling this film thickness in EHL. I'll also show some example to how to use the equation. Can we then predict the risk of damage in a bearing, for example? Well, we can do that to some degree if we can predict the minimum lubricant film thickness, as I showed. If we can say something about the lambda parameter, the film parameter, then we can, with some experience, we can use that to say if there is a risk of different types of damage. We also need to determine the maximum contact pressure. Then in an EHL contact, we may use the contact mechanics equations for dry contact to get a good estimate. Even if it's lubricated, we can use the dry contact expressions for that. And can we then predict the film thickness? Well, we can do that for line contacts and elliptical contacts. And as I said, for Hertzian pressure equations, we can compute the contact pressure. We can even correct it for thermal effects. If you have a sliding contact like in a gearbox, then you need to correct it for thermal effects. You may also need to correct it for roughness effects. Let's start with the conformal contacts. This is a graph from a work from, it's now something like 60 years old, and it's actually made by my PhD supervisor's supervisor in the 60s, Leif Floberg, and he made this fantastic graph, still used in textbooks here in Sweden for hydrodynamic lubrication. So it's a non-dimensional diagram showing it's a non-dimensional load versus the relative eccentricity in the bearing. So when the shaft is operating exactly concentric in the center of the bearing, the eccentricity is 0. When it's in contact with a bushing with the bearing, it's 1. So then it's possible to compute the load carrying capacity for different this is it's a length to diameter ratio for different widths of the bearing. So just an example here, that you have a bearing with a diameter of 200 millimeter, a length, a width of 100 millimeter. Assume that you have a radial clearance of 150 micrometer, a lubricant viscosity of 0.021 Pascal seconds, and a speed of 3,600 RPM. This is a typical turbine example, or steam turbine example. Can we then compute the minimum film thickness? Well, yes, of course, we can determine the P naught here first by just putting the numbers in here. This symbol psi is simply the ratio of the clearance over the radius of the shaft, the journal. So putting the numbers in here, we can compute the P naught to 0.71, and then we just read the newest, and since we have a length to diameter ratio of 100 divided by 200, we use the curve of new 0.5 here, and we use the 0.71 here, and we find that the relative eccentricity will then be 0.54. Okay, if we know the relative eccentricity, we can compute the minimum film thickness according to this expression, and it ends up with 69 micrometers. And normally the roughness here in a bearing like this is something like 1 or 2 micrometers, and that means that the lambda parameter is something like 50 or so. So it's very high. So in this case, we are very sure that we have full film lubrication, and we must have it's a turbine that will operate for years, and we mustn't have a mixed lubrication in such an application. So, but I just wanted to show that it's easy to compute or estimate the film thickness in a journal bearing like that. Of course, in more complex designs like this one, this is a bearing in a hydraulic motor. You have a piston here, and inside the piston you have a roller, and this roller is lubricated. It's like a journal bearing here too, but it's a complex geometry. It's not rigid anymore, really. It's pretty flexible here and here. So then you need to use some finite elements or some kind of multiphysics software to solve this lubrication problem. And here we have been doing that. And of course, if you use that tool, you can compute the minimum film thickness and compare it to the surface roughness, and then you can determine the film parameter and then also estimate the regime it will operate in. I can. You please read this paper by Isaacson or another paper by Salin and co-authors about the mixed lubrication model we have been using here. So in this case, we can actually model not only the full film lubrication, but also when the bearing operates in mixed lubrication. Okay, that's about conformal contacts. Now let's talk about non-conformal contacts. So I will only speak about hard EHL here. So that's the typical contact of steel to steel contacts, like in a bearing or in a gearbox. I will show you directly some equations for that. But first, let's have a look on the generalized EHL problem. EHL is elasto-hydrodynamic lubrication. So assume that you have two rollers like this, two cylinders in contact. you apply a force, a contact force, we denote it by W. We put some speed onto the surfaces, so you have speed U2 on one surface and U1 on the other one. We assume that we have some radius, R2 and R1 on of the cylinders, and we have elastic properties described by the Young's modulus and the Poisson number on both rollers. Then we put the lubricant in here, and what we need to know is the viscosity at atmospheric pressure, and we need to know the pressure viscosity constant, alpha. And so, to summarize, for this, for an EHL contact like this, you need a load, you need the speeds of the surfaces, you need the radius of the two cylinders, you need the viscosity and the alpha, you need the elastic properties, Young's modulus and Poisson number, and in order to compute the film parameter, the lambda number, you need the surface roughness. You may also need the hardness, because you want to see if the contact pressure, if you also compute the contact pressure by using the Hertz analysis, you want to compare that pressure with the hardness to ensure that you don't reach a pressure higher than the hardness. Then you may have permanent damages like plastic deformation of the surface. In order to take the heating into account too, you also need the viscosity temperature relationship. In this case you use a beta number, coming back to that, and you also need the thermal conductivity of the lubricant. Okay, so how do we compute this film thickness then? Well, we need to solve a pretty complex numerical problem. It's a problem where you solve the Reynolds equation. You have in the Reynolds equation you see here that you have something called H, which is the film thickness distribution, and the film thickness is given by this expression. You see here this is describing the cylindrical shape of the contact, and this is the deformation of the surfaces, because we have an elastohydrodynamic contact here. That means the surfaces are deformed. The deformation is given by this expression, and look here now, in order to compute the deformation we need the pressure, but in order to compute the pressure we need the film thickness and the deformation. So this is a non-linear problem. We also need the viscosity, and again the viscosity itself is pressure dependent, which is the same for the density, which also is pressure dependent. And finally, we also need to solve the force balance equation. So the pressure we have been computing should balance the applied load. Note here that it's a W prime here. That means it's a load per meter. So it's an infinitely wide contact. Over the years, a number of people have been solving this numerical problem, and they have been summarizing the results in equations like this, and by using some different regression techniques. In this equation then, which describes the film thickness, or the minimum film thickness in an EHL contact, you can see some numbers here. So it's the R, for example, which is the effective radius of the two cylinders, computed like that. You have the entrainment speed, which is the average speed, simply the average speed, U1 plus U2 divided by 2. You have the viscosity, you have the Young's, or the effective Young's modulus, which is a combination of the two surfaces, elastic modulus and Poisson number. You have the alpha, and you have the load per unit length. So by just knowing the radius, speed, viscosity, elastic properties, alpha and load, you can directly compute the minimum film thickness. And this equation is relatively accurate. It's When I say accurate in tribology, I mean plus minus 20% or so. So it's but for the purpose of determining the film parameter, it's very useful. If you have an elliptical contact, which more generalized 2D contact instead of the 1D line problem, you can use this equation instead. So here you see you have the same numbers, R, in this case it's Rx, which is the radii in the rolling sliding direction only. It's the speeds, it's the viscosity, the elastic properties, the alpha, and the load. In this case it's the real load in Newton. But then you have some additional term here to take care of the ellipticity of the contact. And you have a K here, which is simply a ratio telling you how elliptical this contact is. Again, this equation is only valid for non-conformal hard EHL. It's not valid for soft EHL, like an elastomer in contact with some other soft surface. Okay, let's show an example here. You can, if you want, you can stop the video here and try to compute the minimum film thickness by using the equation I showed in the previous page, or we can just go on and doing that. So we put the numbers here. We can assume it's a steel contact, apply a load of 1000 newtons, radius here is 35 millimeters. It's a pretty big ball in this case. Viscosity 45 millipascal seconds. A typical alpha is like this, and the speed, let's say it's only 0.1 meters per second. So putting the numbers into the equation, first solving the Hertz problem. Please check the contact mechanics video for that. Then we find out that the maximum pressure is something like 1.3 gigapascals. We see that the contact diameter is 1.2 millimeters, and we can compute the minimum film thickness to 0.041 micrometers. So it's, in this case, it's only 41 nanometers. So even if the load is relatively low in this case, it's the film thickness is still pretty small. So it's a relatively thin film, and that's probably because of the low rolling, or the low entrainment speed in this case. Okay, that's the typical EHL film thickness equations. I want to say one thing here, one important thing here. It's that it's actually what is happening in the inlet that controls the thickness of the film. As you recall, the viscosity inside the EHL contact becomes very high in here when it's pressurized to gigapascal levels, and it can't really escape when it's in here. It can't escape. So what is coming in here must also come out. It can't disappear through the surfaces, for example. So that means that what is captured here at the inlet is determining how thick the contact will be. So, and then it's important to discuss inlet shear heating. If you have, this is maybe a better figure showing how it really looks like. The contact zone is only here, but it's a pretty narrow film, or pretty thin film, also in a long distance before the contact. So you shear the lubricant here, and this shearing, especially when you have different speeds of the surfaces, like in a rolling sliding contact, which you can find in a gearbox, for example. When you have different speeds, you have shearing, and that heats up the lubricant very much, and that means that the viscosity here, when it enters the EHL contact, is not as high as it was here in the bulk lubricant. So it may have been increasing in temperature, say 10 degrees, and that means that the viscosity is much lower then. So it could be just 50% of the original value. And this must be taken into account when you have when you use those equations for a gearbox. In order to compute the effect of inlet shear heating, you can use an equation like this. So here you have you need to compute the correction factor CT. CT is a number between 0 and 1, and you multiply that CT by the minimum film thickness obtained from the film thickness equations I showed before. And the CT is given by this a little bit complex expression. It's from a classic work from the 90s. And what you really need here is the Brinkmann number, and you need a slide to roll ratio, you need the Hertz pressure, and effective elastic modulus. The Brinkmann number is given by this expression. You need the temperature viscosity coefficient beta, you need the viscosity under atmospheric pressure, you need the entrainment speed, and you need the thermal conductivity. So the higher the Brinkmann is, the lower the CT will be, so the more heating you will have. The same goes for slide to roll ratio. The slide to roll ratio tells you about how much sliding you have, and the more sliding you have, the more heating you will have too. So in order to compute the CT, you need two additional lubricant parameters. That's the beta and the lambda here for the thermal conductivity. And those are given by well, you can see it from the supplier of the lubricant. Of course, you can ask for a graph of the viscosity versus temperature. But typical numbers for the beta at 40 degrees I've given here. You see that the mineral oils have pretty much bigger numbers than the like esters, and also which have a relatively low number. So that means that the viscosity doesn't fall too much or too fast, and that's good then for the heating. The smaller this number is, the less inlet shear heating. Please note that this temperature viscosity relationship is not perfect, but it's good enough for a certain temperature interval. The thermal conductivity is measured over the years by different people, and this is from a work. It's measured at Umeå University. And you can here also see the thermal conductivity, how it varies with pressure. But in this case, when you are using it for the thermal correction, you only need to find the numbers at atmospheric pressure, because at the inlet you have atmospheric pressure, so zero pressure. So that means that you don't need to take the pressure dependence into account. But you can see here from this graph that the thermal conductivity increases when you increase the pressure, so it doubles more or less, or even more. But you can also see here that the lubricant type or the base oil type is having some effect. So mineral oils typically have lower thermal conductivity, while esters, synthetic esters, have higher numbers. And that also means that the esters, if you have a higher thermal conductivity, more heat is conducted away from the contact, and that means that the EHL contact operates cooler, and you have a thicker film of that reason. On the other hand, the ester has a lower alpha, so the film thickness becomes thinner of that reason. So, but you need to solve the problem. You need to use the equations to get a good estimate. And that's all about film thickness in conformal and non-conformal lubricated contacts. I also recommend you to watch the videos on fundamentals of EHL, lubricants, and lubrication regimes. Thank you very much.